Welcome to the 11th lecture of module 4. In this module, we are discussing reactor design. Before going to this lecture, let us have brief recap on the topic or on the reactor design in this module which we have covered so far. Up to the last lecture, we have covered introduction to the reactor design, and where we have considered three idealized reactor: ideal batch reactor, ideal plug flow reactor and ideal continuous star tank reactor or mixed flow reactor. So, this design of three ideal reactors we have covered. Then we have considered reactor design for single reaction, and when we considered single reaction, we have only concerned about the size of the reactor. We were not concerned about the product distribution. So, that we have covered. Then we have considered multiple reactions. When we have multiple reactions, we mainly concentrated on the product distribution instead of their size requirements. So, product distribution is important in case of the multiple reactions, and we have considered that for the reactor design of multiple reactions. In this lecture, we will cover mainly the temperature and pressure effects. So, the temperature effects and pressure effects so far we have not considered in the reactor design, and we have considered only the isothermal reactor design part. So, now we will consider the temperature and pressure effects for the reactors. As you know, for most of the chemical reactions, either they are exothermic or endothermic in nature. So, they are involved with the heat effects, either it cool down the systems or it will heat up the systems. So, how they affects the reactor design, that we will consider in this lecture. First, we will consider heat of reactions and equilibrium conversion from thermodynamics. So, the brief lecture outline would be introduction to temperature and pressure effects. Then we will consider heat of reactions from thermodynamics. Then we will consider energy balance equation, and then we will consider equilibrium constant from thermodynamics. While doing so, we will mainly calculate the equilibrium conversion. So far, what we have considered? We have considered how reactor type and size influence the extent of conversion and distribution of the products. So, this we have considered in the reactor design part in module 4, the type of reactor and the size of the reactor, how they influence the extent of reaction and the product distribution. And initially we considered single reactions, and later we have considered multiple reactions where we were more concerned about the product distribution. What we need to consider now? We need to see how the reaction temperature and pressure, these two influence the progress of the reaction. So, influence of temperature and pressure, we need to see about the progress of the reaction. We can follow a 3-step procedure. What are them? First, find out how equilibrium composition, rate of reaction and product distribution. These three affected by change in the operating temperature and pressure. So, initially we have to find out the equilibrium composition, rate of reaction and product distribution, which with change in operating conditions like temperature and pressure. This will allow us to determine the optimum temperature progression. So, with increase of temperature how they are changing, and then from that we can calculate the optimum temperature, how they progress for every steps. Secondly, we need to see how heat effects will change the temperature of the reacting systems. So, when there is a chemical reactions, it generally involves heat effects, either it absorb heat or it released heat. When it absorb heat we call endothermic reaction, when it evolve heat we call exothermic reaction, and this change of heat effects, how they change the temperature of the reacting mixture, that we need to analyze. This will help us to propose a number of favorable reactors and the heat exchange systems which closely approach the optimum. So, based on these heat effects we can see what are the favorable reactors to operate and which heat exchange system, whether we need to use heat exchange systems for this purpose, that we can propose, which will closely resemble to the optimum operating conditions. And finally, economic consideration will select one of these favorable systems as the best. So, from the multiple favorable conditions or reactor systems, if we propose, and finally the economic consideration will choose one of them as the best one. Now, if we have single reaction, then for single reactions, as we have discussed earlier, we are mostly concerned on conversion level it can achieve and the reactor stability, whether the reactor is stable up to that operating conditions. But we are not concerned about the product distribution, which is not applicable for the single reaction. Now, two important informations we can get from thermodynamics. One of them is heat liberated or absorbed for a given extent of reactions. So, for a chemical reactions to proceed up to a certain extent of reactions or certain conversion level, how much heat it absorbs or how much heat it liberates due to the chemical reaction, that information we can obtain from the thermodynamics. The second important information we can get the maximum possible conversion in a given reactions. This is generally happens in case of irreversible reactions, the increase of temperature will increase the conversion level, whereas in case of reversible reaction there is some equilibrium conversion at particular conditions. So, what would be the maximum possible conversion that we can obtain from the thermodynamics? This maximum achievable conversion is theoretical considerations from the thermodynamics, and that is the maximum limit. In real systems it is in general it does not achieve to that extent. So, that is only from the theoretical consideration in viewpoint of the theoretical considerations. Now, heat of reaction from thermodynamics. So, heat of reaction from thermodynamics, the heat which will be absorbed or liberated during a chemical reaction will depend on the three factors. One is nature of the reacting system, secondly, it will depend on how much amount of material it is reacting. So, amount of material reacting and the third important thing is that the temperature and pressure of the reacting systems. Temperature and pressure of the reacting system. So, these are the three factors on which it will depend the amount of heat released or absorbed during a chemical reaction. Now, when these three factors can be calculated if we know the heat of reaction. So, if we know heat of reaction, then we can calculate based on this how much heat it will be absorbed or liberated during a chemical reactions. If this is not known, then we can calculate from the tabulated data on the heat of tabulated data which is on heat of formation that is delta HF or heat of combustion. That is delta HC. These are for the reacting material. And these data are generally tabulated at a certain standard conditions which is generally at temperature T0 or T1 certain standard temperature and at 25 degree centigrade usually. So, when delta HR is not known, then these two are calculated from the tabulated data. Now, let us consider the reaction A mole of A is disappearing or dissociating, forming R mole of R plus S mole of S. So, we can define for this chemical reaction the heat of reaction is defined at temperature T as the heat transferred to the reacting system from the surroundings when A moles of A disappear to produce R moles of R and S moles of S with the system measured at same temperature and pressure before and after the chemical reaction. So, this is say we can write for this reaction delta H are at a temperature T, this is generally positive for endothermic reaction, and this is negative for exothermic reaction. So, positive for endothermic reaction and negative for exothermic reaction, delta HRT, that is heat of reaction at a temperature T, and this heat is defined. So, the amount of heat transfer from the surroundings to the reacting systems, and when these reactions happens as per their stoichiometric composition, and the system would be measured at the same temperature and pressure before and after the chemical reaction. Now, our first problem is to evaluate the heat of reaction, and knowing some values of heat of reactions at temperature T2, we need to calculate some temperature T1, we need to calculate at temperature T2. So, this can be done with the help of energy balance equation. So, say heat absorbed during chemical reaction at temperature T2 would be equal to heat added to reactants to change their temperature from T2 to T1 plus heat absorbed during reaction at temperature T1 plus heat added to products to bring them back to T2 from T1. So, this is the energy balance equation, and in terms of the enthalpies of the reactants and products, we can write this as delta H R2 would be equal to minus H2 minus H1 reactants plus delta H R1 plus H2 minus H1 products. So, 1 refers to subscript 1 refers to temperature T1 and subscript 2 refers to temperature T2. So, this energy balance expression we can write in terms of the specific heat delta H R2 we can write as delta H R2 is equal to delta H R1 plus integral T1 to T2 delta Cp dt, where delta Cp is equal to R Cpr plus S Cp S minus A Cp A. So, these are the molar specific heat. These are molar specific heat and these are basically function of temperature. So, we can write Cpa is equal to alpha A plus beta A T plus gamma A T square. So, is a function of temperature. Similarly, other can be written as a function of temperature. Cpr is alpha R plus beta R T plus gamma R T square, and Cps is equal to alpha S plus beta S T plus gamma S T square. Now, if we substitute this Cpr and Cps into this delta Cp, we would obtain this energy balance relations would be delta H R2 is equal to delta H R1 plus integral T1 to T2 delta alpha plus delta beta T plus delta gamma T square into dt, and which would be this delta alpha is nothing but R into alpha r plus S into alpha s minus A into alpha A. Similarly, delta beta is equal to R beta r plus S beta s minus A beta A, and delta gamma is equal to R gamma r plus S gamma s minus A gamma A. So, this can be integrated and we can obtain delta H R 1 plus delta alpha into T 2 minus T 1 plus delta beta by 2 T 2 square minus T 1 square plus delta gamma by 3 T 2 cube minus T 1 cube. So, knowing the heat of reaction at any one temperature and the specific heat of reactants and products, we would be able to calculate the heat of reaction at any other temperature. So, this is the relations between heat of reaction, temperature and specific heat. So, equilibrium constant from thermodynamics. The second law of thermodynamics allows us to calculate the equilibrium constants and hence the equilibrium composition and the equilibrium composition of the reacting systems. But this real system, as we have discussed earlier, the equilibrium conversion which we obtained from the thermodynamics is basically attainable value which is suggested by thermodynamics. It generally does not achievable in the real systems. So, if we consider the standard free energy delta G, delta G naught, and if we consider the reaction AA2 RR plus SS, this reaction we can define at temperature T delta G 0 can be written as R G R naught plus S G S naught minus A Ga naught, which is equal to minus R T ln K, which is equal to minus R T ln F by F naught to the power R F by F naught to the power S divided by F by F naught for A to the power A. So, this F is the fugacity of component at equilibrium conditions. And F naught is the fugacity of component at any arbitrarily selected standard state. At temperature T, and G naught is the standard free energy of a reacting component. And K is the thermodynamic equilibrium constant for the reactions. K thermodynamic equilibrium constant. Now, this standard state can be defined at a given temperature for gases pure component at atmospheric pressure, and if it is solid, pure solid at its unit pressure, and liquid, pure liquid should be at its vapor pressure, and if it is solute in liquid, then 1 molar solution is considered as the standard state. So, these are available in the textbooks, the standard conditions we can consider. Now, for convenience we can define Kf in terms of the fugacity, the equilibrium constant we can define Kf would be F R to the power R, Fs to the power S divided by Fa to the power A. We can write in terms of pressure. So, Kp would be equal to Pr to the power R Ps to the power s divided by Pa to the power A. We can also write in terms of the mole fraction, that is Ky, which is equal to y r to the power r y s to the power s divided by y a to the power a. We can write in terms of concentration as well, that is K c, which is equal to C r to the power r C s to the power s divided by C a to the power a. And delta n we can write as r plus s minus a. So, this is the change of mole between the products and the reactants. Now, for gaseous system we can consider the standard state is 1 atmosphere, and since the pressure is low, which is atmospheric pressure, generally the fugacity and the pressure are same. So, at gas phase reactions at 1 atmospheric pressure, we can write fugacity is equal to pressure, which is equal to 1 atmosphere. And so, K can be written as e to the power minus delta G naught by RT, which is equal to Kp at into P naught is equal to 1 atmosphere to the power minus delta n. So, this term is always unity, but it was kept with the equation to make it dimensionally correct. So, now if we consider ideal gas, we can write Fi is equal to Pi, which is equal to Yi into pi, which is equal to Ci RT. So, we can write Kf is equal to Kp, and K we can write Kp by P naught is equal to 1 atmosphere to the power delta n, which is equal to Ky pi to the power delta n divided by P naught is equal to 1 atmosphere to the power delta n, which we can write Kc RT to the power delta n divided by P naught is equal to 1 atmosphere to the power delta n. And if we take solid components taking part in the reactions, for solid F by F naught would be equal to 1. So, that means the fugacity variation with respect to the pressure in case of the solid is negligible. So, F by F naught for solid component can be considered as 1. Now, we will see how we can calculate the equilibrium conversion from thermodynamics. The change in equilibrium constant with respect to temperature is defined as d ln k dt is equal to delta H r divided by R T square. Now, if we integrate with a temperature limit T2 and T1, we can calculate ln K2 by K1 is equal to minus delta H r by R 1 by T2 minus 1 by T1. So, R is the universal gas constant, T is any temperature here, and while integrating it is assumed that delta H r is considered as constant in this temperature range, and hence taken out from the integral sign. So, this is from where, knowing the K1 at a particular temperature, we can calculate K2. Now, if there is variation of delta H r in the temperature range, that should be accounted for. So, we can write in that case ln K2 by K1 is equal to 1 by R integral T1 to T2 delta H r divided by T square dt. Now, this delta H r, if it is temperature dependent, then it can be written as delta H r naught plus integral T naught to T delta Cp dt. Now, if we substitute this delta H r over here and then putting the values of delta Cp which we have obtained earlier, and then we can integrate, and the integration will give R ln K2 by K1 would be equal to delta alpha ln T2 by T1 plus delta beta by 2 T2 minus T1 plus delta gamma by 6 T2 square minus T1 square plus minus delta H R naught plus delta alpha T naught plus delta beta by 2 T naught square plus delta gamma by 6 by 3 T naught cube into 1 by T2 minus 1 by T1. So, these relations will help us to find out the equilibrium constant and hence the equilibrium conversion with the change in temperature. Now, let us take an example. So, consider the following elementary reaction, say A2R, this is reversible reaction where delta G naught at 298 is given minus 1413 joule per mole and delta H naught at 298 degree centigrade 298 Kelvin is given as minus 75,300 joule per mole, and Cpa is equal to Cpr is equal to constant. Now, we need to determine the equilibrium conversion between 0 degree centigrade and 100 degree centigrade, and then plot the temperature versus conversion. Second is what restriction should be placed for the reactor operating isothermally if we are to obtain a conversion of 75% or higher. So, let us solve it. As we can see, the specific heat Cpa and Cpr, so these are given constant. So, since Cpr and Cpa is constant, so delta Cp would be equal to 0. So, that means the heat of reaction delta Hr is independent of the temperature. So, in that case we can write delta Hr would be equal to delta H R at 298, which is equal to minus 75,300 joule per mole. Now, we can calculate the equilibrium constant at 25 degree centigrade from the equations which is known, K is equal to exponential minus delta G naught at 298 by RT. So, now if we substitute, this would be exponential delta G naught 298 is given. So, which is 1413 naught joule per mole divided by R is universal gas constant, which is 8.314 joule per mole Kelvin into T is 298 Kelvin. So, this would give about 300. Now, since the heat of reactions do not change with temperature, the equilibrium constant at any temperature T, we can write ln K by K 298 would be equal to minus delta H R by R into 1 by T minus 1 by 298. So, if we rearrange this, we can write K would be equal to K 298 exponential minus delta H R by R into 1 by T minus 1 by 298. Now, if we substitute the values K 298 we have calculated, which is equal to 300, and delta HR is equal to minus 75300 joule per mole. Now, if we substitute this in this relation, we would obtain this is 300 exponential seven five three zero zero divided by 8.314 into 1 by T minus 1 by 298. So, if we multiply, it would be 300 into exponential 75300 by 8.314 T minus 30.393. So, using this expression, if we choose a different temperature, we can calculate K values. Now, at equilibrium, K is equal to Cr by Ca, which is equal to Ca naught x AE is the equilibrium conversion divided by Ca naught into 1 minus XAE, which is equal to XAE divided by 1 minus XAE. From here we can write XAE is equal to K by K plus 1. Now, with these two relations we can calculate K first at a particular temperature, and using that K values we can calculate the XAE values. So, we can obtain the table, say at selected temperature K is equal to 300 into 75,300 divided by 8.314 into T minus 30.393. This is exponential. Then we can calculate XAE is equal to K by K plus 1. So, at a selected temperature, say 5 degree centigrade, and which is temperature we can make it say degree centigrade and Kelvin. So, if it is 5 degree, then it is say 278, say 15 288, say 35 308, we can 55, say 328, we can do 75, which is 348, and say 95, say 368. So, these are the temperatures say at a particular interval we can select, and we can put into this equation. So, we can obtain, so this is about 2700, and this is about 860, then this is about 110, this is about 18.4 or 18, and this is about 3.8, and this is about 0.92. So, the corresponding values we can calculate XAE, putting these K values over here. This would be point close to 1, and this is about 0.999, then this is about 0.991, this is 0.949, this is about 0.791, and this is about 0.48. Now, we can plot the conversion versus temperature. Say if we plot say degree centigrade and in temperature and the conversion, we would obtain say this is 0 0 and this is temperature in degree centigrade, and say this is 0 and this is 20, say 40, 60, 80, 100, 120, 140. So, 20 is 20, 60, 80 and 100. Conversion is 0, then 0.2, 0.4, say 0.6, 0.8 and 1. So, our conversion starts at a very low temperature, say 5 degree. So, it is close to 1 and conversion starts like this and it goes down and like this, say up to 0.4. So, now we can, so this is the XAE, equilibrium conversion versus temperature plot. Now, so the first problem is we can determine the equilibrium conversion between this temperature 0 degree centigrade to 100 degree centigrade. So, in between, and we can plot the temperature versus conversion plot. Now, what restriction should be placed for the reactor operating isothermally if we are to obtain a conversion 75% or higher? Now, at 75%, say it is very close to over here, and we can locate the equilibrium conversion, which is close to so if we go from here to here and come down. So, this temperature is about equilibrium conversion at this 75%. So, this is 0.75%, 75% conversion. So, this temperature T is about 78 degrees centigrade. So, if we had to achieve this 75% conversion or higher, we had to be below this temperature. That means, the T should be less than 78 degree centigrade. Now, what conclusion we can make from the thermodynamics? We can see that thermodynamic equilibrium constant is unaffected by the pressure of the system, presence or absence of the inert and kinetics of the reaction. So, these three parameters, pressure of the system, inert and the kinetics of the reaction, this does not influence or these are unaffected the equilibrium constant. So, but the equilibrium constant is affected by the temperature of the reacting system. So, although the equilibrium constants are unaffected by these parameters, but their equilibrium concentration of the material and the equilibrium conversion does influence by these three parameters: pressure of the systems, presence or absence of the inert, and kinetics of the reactions. So, these three parameters influence the equilibrium concentration of the materials and the equilibrium conversion. Now, if we see the equilibrium conversion versus temperature plot as we have done before, we can see that for exothermic reaction we have seen the equilibrium conversion drops with increasing temperature. Whereas, for endothermic reaction it increases with temperature. So, this is for K very greater than 1 and this is for K very less than 1. So, this is for exothermic, this is for endothermic reaction. So, K very greater than 1, it indicates that practically complete conversion may be possible and reaction can be considered to be irreversible. So, this can be considered as irreversible reaction. K very less than 1 indicates K very less than 1 indicates the reaction will not proceed to any appreciable extent. So, which is the case in case of the, so this is for exothermic reaction. So, that is very low conversion as we increase the temperature. Now, with increase in temperature, the equilibrium conversion increases for endothermic reaction and equilibrium conversion decreases for exothermic reaction. With increase in pressure for gas phase reaction, what we can see that conversion increases when the number of moles decreases with reaction and conversion decreases when the number of moles increases with the reaction. This is the case when we increase the pressure for the gas phase reactions, whereas a decrease in inert for all reactions acts in the way that an increase in pressure acts for gas phase reactions. So, in this case the effect of inert can be seen for all kind of reactions. If we decrease the inert, it will act in the same way as with increase in pressure for the gas phase reactions. So, with this we conclude for the lecture 1 for the calculation of the equilibrium constant and variation of the temperature or calculation of the heat of reactions from the thermodynamics point of view. We will continue our discussion for temperature and pressure effects in the next lecture. Thank you.